Welcome everyone to this demonstration. In the next 5 minutes, I'll walk you through the essential steps of setting up and running a CFD simulation in STAR-CCM+. We begin by launching the STAR-CCM software. STAR-CCM is a client-server application. The user interface you see here is the client, which communicates with a server process that handles the simulation. To start a new simulation, we'll go to the File menu and create a new server process. Once the server is started and the software license is validated, you'll notice the simulation object tree appear in the Explorer pane on the left. Next, I'll import the geometry of our simulation. In this case, we have an STL file containing the geometry of a branched pipe. As you can see, the imported geometry is now displayed in the graphics window. You can use the mouse and keyboard controls to rotate, zoom, and pan the view. Next, we need to identify and name the part surfaces according to their boundary conditions. This is done by splitting the original surface using a split surfaces operation. Here, I am using the split by angle option, but there are many ways to do so. You'll see that now, instead of one boundary surface, there are 4, as needed to appropriately define the inlet, outlets, and walls of the pipe. With the part surfaces delineated, we can now convert the geometry parts to regions and boundaries. This is done by right-clicking the original pipe part and assigning parts to regions. I'll choose the appropriate subselections in the dialog box, and the object tree will update to reflect the new regions and boundaries that have full associativity with the original parts and surfaces. The next step is to assign the boundary types to our region boundaries. We'll assign the inlet boundary as a velocity inlet boundary type, and the 2 outlets of the pipe we will assign pressure outlet boundary types. The default boundary type is a wall boundary type, so our pipe walls do not need to be edited. To define the physics of our simulation, I'll right-click the Physics 1 node and choose Select Models. In the Physics Model Selection dialog, I will select the appropriate models for our incompressible turbulent airflow simulation. These include the 3D model, the gas flow model, the segregated flow model, the constant density model, the turbulent flow model, and the K-epsilon turbulence model. With the geometry, physics, and boundary types set, I can now generate the volume mesh. I start by creating an automated mesh operation by right-clicking on our original part and selecting Automated Mesh Operation, followed by dialog box selections for employing a surface remesher and trim cell volume mesher. I'll ensure that we are meshing in parallel across multiple compute cores. I'll define a few global meshing parameters, and then finally click the Generate Volume Mesh button to start the meshing process. The progress will be displayed in the outlet window. Once the meshing operation is complete, I can note that our mesh contains 12,540 cells. I will also revisit my original scene and turn on a displayer for visualizing the mesh produced on the pipe walls. This provides me with an intuitive grasp of the mesh quality I have achieved with my previous model selections. Boundary condition definition is critical for accurate simulation. I'll proceed to setting the inlet boundary a velocity of 10 meters per second and the outlet boundaries a pressure equal to that of ambient, which is the default. To monitor quantities of interest during the simulation, we use reports. Here, I am defining a pressure drop report from pipe inlet to outlet boundaries by right-clicking on the Reports folder in the Explorer pane and making the appropriate subselections in the Properties window. By right-clicking on the new report, we can choose to create a monitor and plot from this report, after which a new plot scene is created and opened, and where we can track the pressure drop calculated as the simulation progresses. To visualize the flow, I'll use a vector displayer to be viewed in our existing geometry scene. I'll start by removing the mesh displayer and reducing the opacity of the pipe walls so that we can visualize what is happening inside of those walls. Right-clicking the Derived Parts folder of the Explorer plane allows me to create a new plane section through the horizontal symmetry plane of our system, and additionally generate a new vector displayer associated with this plane in the geometry scene. I prefer to view the line integral convolution style of vector displayer. Finally, I'm now ready to run the simulation. Clicking the Run button will start the solver, and the residual plot will show progress towards convergence. As the residuals and quantities of interest flatten out, it indicates that the CFD solution process is converging. Once convergence is reached, I can examine the results in the scene. And there you have it. In this demo, we've covered the basic workflow of setting up and running a CFD simulation in SimCenter STAR-CCM+, from launching the software to visualizing the final results. Hopefully, this has provided you a brief glimpse into the capabilities of the software, and you now feel excited to jump headfirst into the hard work of building your CFD skills.